First of all, I would like to thank you for your attention to this webinar. And I'm very happy to be here with Marit and with Paul. And we will share the moderation of this webinar. In case that you have technical problems, then please let us know either by the chat, what means that you are already in, or by an email, so that we maybe can try to help you to still get in. There is a chat function in this webinar software. Please use this. You can write chats directly that I will try to answer during the webinar. If you would like to have things answered publicly later on, please put it into the F&A, questions and answers section, and we will take care to answer these ones at the end of the webinar. So I would like now to give the words to Marit and to Paul, and please start.
Thank you, Andreas. My name is Marit Jarvik, and I am a PhD student at the Bundesanstalt für Materialforschung und Prüfung, and I am writing my PhD thesis in cooperation with SPECS.
Hello, I'm Paul Dietrich. I'm an application scientist here at SPECS. I also want to welcome you and give you, in the beginning, a short overview of the webinar today. So it's about ambient pressure XPS on biofilms and bacteria. The agenda is following. And first, we get a short introduction by Andreas about the EnviroESCA machine and its features and some application examples. Quite a severe echo there. Okay, sorry. Maybe from your microphone.
Turn off your microphone.
Okay, I can try to switch off.
So maybe it's the second microphone from Andreas. The second one is a demonstration of a standard measurement on a gold sample. And the third will be the main feature of the webinar. It's about the sample preparation of bacterial and biofilms. And in the end, we will have a demonstration of a live measurement of E. coli samples at different pressures of water vapor. And with that, I would give over to Andreas, and he will start a short introduction of the EnviroESCA.
So I switched my microphone on again. Is it well to hear now, or is there also an echo on my microphone now? So I will just start to talk, and if there is an echo or some problem to understand me, then please let us know. So the machine that we used for the project is the EnviroESCA, and this is a tool for surface chemical analysis under environmental conditions. And it was especially designed to make this technology easy and fast, what made it a perfect instrument to use during a European project working on bacteria and biofilms. The word ESCA comes from electron spectroscopy for chemical analysis and is another name for X-ray photoelectron spectroscopy. And this all is done as written here under environmental conditions. But first I would like to show a little bit, but not too much in detail, how photoelectron spectroscopy works. So first of all, of course, you need a sample. And in a standard XPS experiment, this sample is sitting under ultra-high vacuum conditions. And the sample is sitting in front of the entrance of an analyzer. And what you then do next is that you, from an X-ray source, from a monochromatic X-ray source, you illuminate an analysis region on your sample area with X-rays, and these X-rays make a photo effect there, and this means that they excite photoelectrons, and these photoelectrons are then moving into the analyzer entrance, and inside this electron analyzer, they are assorted according to their kinetic energies. And the kinetic energies that they carry also the binding energies of the electrons in the solid or in the material. And by this, you have a chance to do chemical analysis. So this means this is a technology where you get a chemical composition of your sample surface, because it's a surface-sensitive method, and you get a certain amount of electronic information also. The good thing is that this method is mostly non-destructive. It is a pretty quantitative method with a sensitivity down to something between 0.1 and 1 atomic percent, depending on the element that you are analyzing and the matrix. And it is a surface-sensitive method. And this combination of properties or chances by this method makes it a very successful method. And this is shown by this view graph here. This shows the number of publications per year of XPS or ESCA papers in comparison with papers published on Auger spectroscopy and SIMS. So where you see that Auger and SIMS is pretty constant over the years, while XPS is really an increasing technology with increasing interest and with increasing number of publications per year. This view graph ends at 2012, but still this trend goes on. I don't have the actual view graph on hand, but we know that this trend is just going on. This is a pretty nice method, especially for conductive samples and especially for solid samples. This method shows or starts to show limitations when you would like to do and analyze materials where you have to do some treatments under ambient conditions. And this is shown now in this view graph here. The example given here is a paper clip that should be etched in acetic acid. And the goal of this etching step is to remove the nickel layer on top of the stainless steel paper clip. So the first thing that you do is you put the paper clip into the acetic acid, you let it etch for a certain amount of time, then you take it out, you wash it away, the acetic acid, then you dry it out. And then the next step is that you put it into the vacuum of the machine and then you do the analysis. This is shown here. If the etching was successful or not, you only know after this analysis step. So if it were not successful, you have to go back and take the sample out again and do another etching step under ambient conditions. And then you have to do the same. You have to wash it away, clean it, dry it out, bring it into the machine. And each of these steps takes easily 1 hour or more. So that means after 2 hours, you know if the second step was successful. And if not, then you take it out again and you repeat it, and you might repeat it a third time, and you also might repeat it another time. The problem is that you only know if you had success when the sample is back in the machine, but finally, it is also very easily possible that in between some etching steps, you just missed the point where you start to see the interface between nickel and stainless steel. So even if you do this very properly, you still can miss the point and still might not have success. And then you have to repeat all of this procedure and all of this experiment again. And because of these limitations, and this is also a limitation that occurs in other analysis techniques where you would like to learn about the chemical composition of working devices or materials under generic or reactive environments, people started to think if you can maybe do the analysis also during these treatment steps. And what finally was developed is near ambient pressure or ambient pressure XPS, what is the technology behind the EnviroESCA. And this works like this. You still have the same situation as before, but often people are working when they are working in catalysis or when they are working in batteries, they are also working with insulating samples, and especially this is also a topic for today because also the biological samples are insulating samples. And this means when you do photoelectron spectroscopy, you leave behind positive charges and you have to take care to equilibrate these positive charges because otherwise you will lose the chemical information of the electrons coming from your sample surface. And as we have seen, working under ambient conditions means that you have to work under increased pressures. And this means there is a residual gas pressure inside the machine. And this is demonstrated here. And this residual gas has two effects. It has one effect that the residual gas or the residual gas molecules are points where the electrons coming from the sample on the way to the analyzer entrance are inelastically scattered. And if they do so, they lose part or all of their chemical information. So this has to be avoided. And one way to avoid this is to come with this entrance of the analyzer pretty close to your sample surface. And this is done in the standard near ambient pressure XPS machine always, not only in the EnviroESCA. The second thing that these gas molecules do is that the X-ray beam is also exciting the gas. This means what you additionally get is electrons from the gas, so that you also see the gas lines, what is good, because then you know that there is still gas here in front of your analysis region. And the second thing is what is happening is that you have residual electrons and positive charges, and they can help to equilibrate the positive charges here when it is an insulating sample. And by this, the sample can be measured independently if it is an insulator, a metal, or a semiconductor, and if it is a liquid or if it is a gaseous sample. This is all no longer important. You simply can measure it, and you still can do the non-destructive, quantitative, surface-sensitive chemical analysis. And you get out the chemical composition and the electronic properties, but additionally you can work under operando conditions, and operando is limited to something below 100 millibars. This is a technology that is somehow existing since the early 70s, but you see that it is also very much growing in interest over the last years. And the reason for this is the fact that you now can really go for and buy machines that can realize this technology also in the laboratory environment. So what does that mean for our etching experiment? This means you insert the paper clip together with the acetic acid into the machine, and then you come close to your sample with your nozzle. This is the entrance of your analyzer. And then you look for a position where the layer of the liquid of the acetic acid is so thin that you can measure through the acetic acid and still see the paper clip. And when you find this position, then you just etch it, you just wait, and while you wait, you always take the spectra. And this means that you are always taking spectra, means that you cannot miss the point where you stop to see the nickel and start to see the iron. And so this is a perfect method for operando studies, but as I said before, it is also a perfect method for other applications. Looking at the machine is an all-in-one compact machine where you have service accesses here in the housing, where you have here a door where you load your samples. This is all done in the so-called sample environment. And you have everything inside, the electronics, the gas handling, the vacuum system with all the pumps. And finally, when you look into the machine setup itself, then the sample environment is a part that you can take out. And the sample environment is the part that also defines what you can do to your sample while you are measuring. So there can be a special one for a liquid experiment like we just described now. There can be one specialized for battery research with contacts and with counter electrodes. There can be one that is optimized for catalytic reactions with very high temperatures on powders. You also can combine these things in one or two of these sample environments, but you always can exchange them. And the exchange of such a sample environment takes about an hour or 1.5 hours. And still the rest of the system stays functional. So that means the system stays the same and you just redefine what the system should do for you. Inside this is, besides this sample environment, of course, an electron analyzer. This is shown here. And in difference to the standard sample analyzer and electron analyzers, this has pumping stages. This is all connected to a very small analysis compartment here. And the second important part connected to this is the monochromatic X-ray source with a spot size of around 300 microns. And you need additionally digital microscopes, and later on the experiments that we show to you will make clear that you urgently need them for navigation on the sample. Additionally to this, you also can have an ion source mounted for depth profiling. This is something that Marit will describe later on in an Outlook. And also always built in by the gas pressure is this environmental charge compensation. By just letting gas in 1 to 3 millibars helps you to equilibrate your residual charges and make every insulator measurable. So you can also have different add-ons to the machines. So you can integrate it into your laboratory environment by UHV connections, by vacuum or inert gas suitcases, by having a sealed sample container where you can bring in samples and bring out samples to and from glove boxes. You also can, if you want, directly connect a glove box in front of the machine. And if you really have a large number of samples for standard measurements, there's also an optical characterization stage named Sample Explorer, where you can define on each and every sample spot and sample what you would like to measure where. And then you just bring the sample to the machine and it immediately starts to run this program for your different samples and from your sample platter. The sample platter is pretty large, so you can mount samples up to 120 millimeter in diameter, where you can address about 60 millimeter in the middle. Everything is run from software. This is also something that Paul will show you later, how this works and what the software is doing here, but everything is included here. The status, the sample treatment, the positioning of your sample, and also the starting of your analysis, and also the part where you can evaluate your data later on from your taken data. What finally is this machine good for? I have collected some examples. First of all, it is a very nice machine for high throughput analysis. The reason is that the machine does not take care if it is an insulator, if it is a metal. It does not take care if the material that you insert is degassing or not. It just measures it. And this is shown here as an example on a printed circuit board, where we have measured on the gold contact, so you can measure gold. We have measured on the soldering points, where you measured the tin signal, but also you can measure under the same conditions and under the same speed the polymer here, where you can just see that it is an insulating polymer of typical composition, carbon, nitrogen, oxygen. And finally, this all works under, let's say, 1 millibar of residual air pressure. It is also a very nice material for insulating materials and also for strong and inhomogeneous insulators like zeolite. So this is really a bulky piece of zeolite. You see that you can measure it very nicely. And this view graph here shows how the charge compensation works. This is not taken from this zeolite. This is taken from a PTFE standard sample. But it shows that when you work under ultra vacuum conditions, you are pretty well shifted off the fluorine 1s signal from the original position of around 685 electron volts to close to 800 electron volts, and it is pretty broad and asymmetric. So you cannot really analyze this. But as soon as you let 1 millibar, 2 millibar, or even higher millibars of gas in, you see that it shifts back to the original position, but most important is that it also gets very symmetric and that you get a very narrow line so that you really can do chemical analysis here. And the criterion to find out what is the good pressure is, where is the line width the smallest one? And you see that you don't have to go to 5 millibar or higher. You just can pretty easily work under 1, 2, or 3 millibars, where you also see that you do not lose a lot of signal due to the inelastic scattering in the gas phase. Degassing samples are pretty interesting, especially for food industry or for sensitive materials like biological materials, as we see later on. And you can measure them very fast because you do not have to wait for the really huge degassing times that you normally have in ultra-high vacuum machines, where you have to wait for hours until you can measure it. And finally, you measure on something that is no longer the pristine material, or like here, the cheese that we have measured. And of course, it is also a pretty nice tool to measure liquids, gases, and all their interfaces to solids. And this is shown here by a water-soaked superabsorbent polymer, where when you are far away from the entrance of the analyzer, you only see the water vapor signal, so that's the oxygen 1s signal. So you see here water vapor. When you then come close into the measurement position, you see besides the water vapor also the absorbed water inside the superabsorbent polymer, and then you can start to dry out the superabsorbent polymer, where it shrinks until it is completely dried in this stage. And you see that the portion of the absorbed water that you can see in the spectrum is increasing. And finally, you also see increasing the groups, the oxygen-containing groups of the superabsorbent polymer, so that you really can learn how water or liquids are incorporated and absorbed in porous materials. And as I said, you also can work in gaseous environments. So this is a vanadium oxide, pentoxide single crystal, where we wanted to see if you can study surface reactions, and this is easily possible. So you take this, you cleave it in air, and then you put it onto a heater device into the system, and shown here is, as one example, a laser heater, where you have here the status under room temperature conditions, and this is around 1000 degrees C. And we have used a heater to reduce and reoxidize the vanadium pentoxide. So we started with just inserted and freshly cleaved vanadium pentoxide. This is a vanadium 2p signal here. Vanadium pentoxide means, under this stoichiometry, that vanadium is in the stoichiometric compound in 5+ state. This is shown here. When you now start to heat it up in vacuum up to 500 degrees C, then you lose oxygen, it is reduced. And you see that due to the reduction, vanadium is reduced from 5+ to 4+ state. This is what you can see here. And finally, we let oxygen in, 2 millibar of oxygen, and we kept the sample at 300 degrees C. And what you then see is that you reoxidize the vanadium, you lose a lot of the 4+ state vanadium, and you restore the 5+ vanadium here. So this is also a pretty nice experiment demonstrating how you could work in catalytic or surface reactions. By this, I would like to stop with the introduction to the machine. If you have questions, then please let us know later or contact us later on. Thank you.
With that, I would take over from Andreas. Thanks for this nice introduction of the EnviroESCA. The next point would be that I show you shortly how you can measure a standard sample with the EnviroESCA. This will be shown in the following presentation. In this case, we have a standard gold sample, which will be measured at 25 millibars of nitrogen. And here you see the gold sample, which is placed on the standard sample plate of the EnviroESCA, which is then introduced into the sample environment on top of the manipulator. This manipulator has a kinematic mount for this sample plate that you always mount it in the same way and on top of the manipulator. Then you close the door and start the evacuation by clicking on the evacuate button. You can choose the pressure, you can choose the pumping speed, and you can choose also to transfer it automatically after the target pressure was reached. Then you just click start, and the automation starts with evacuating the chamber. What you see here, the pressure goes down, and you also see it in the second part of the software in the live data view, where you can monitor all different values. In this case, it's the pressure of the backing pump and the pressure in the sample environment, which goes down pretty fast. So at the moment then we go down to a few hundred millibars, and if the sample environment reaches a pressure of approximately 25 millibars, the automatic transfer in will start, and then the manipulator starts to drive into the analysis section, which you see here in the camera and the program. And then you will also see it from the outside, from filmed through the door, where the manipulator goes up during transfer in, which is shown here. So here's the sample on the sample plate. This is the manipulator. Here you see some ports for feed-throughs, for electrical measurements or sample current measurements. Then you see some light here, and this is the sample environment, which can be also be adapted to the customer's needs. Now the bellow goes up with the manipulator. Then we will switch back to the software of the EnviroESCA, and you will see how we start the measurement. This can be done automatically or by just selecting the spectra you want to take. This is here shown in the task manager. You click on the spectrum group you want to measure. In this case, it's a gold 4F and the nitrogen line. Then you put start, and then you see how the sample goes to a predefined position just under the nozzle automatically. This now is a working distance of around 300 microns, and the measurement now starts automatically with the preset spectral regions and pass energy. In this case, it's a 550 eV pass energy. And now we see at 25 millibar the gold signal, and this is only a single scan, and this is pretty nice quality of data points for 25 millibar of nitrogen. Additionally, there's also taken a nitrogen spectrum to have the gas line, as Andreas said. You can at the same time check if still is your gas present in your analysis section. If you do it under different environments, then you can check if the gases are present or if something is wrong with the conditions you want to treat your sample with. In this case, it's the nitrogen spectra, and for the gas peak, it's a little bit higher than the literature value of 400 eV. It's around 406 eV binding energy because it's the signal of the molecular nitrogen. And yeah, after the measurement is done, you can do further measurements, or you just say stand by and vent, and then you can choose the venting speed and say vent, and then the sample goes down. Your experiment is finished. For this experiment, it would be pretty easy to have a high throughput measurement, so you can predefine your experiments and then start it up overnight or over lunch, so you don't have to be next to the machine. And with this short presentation ends, and I would hand over to Mara.
Thank you, Paul. So over to the next part of this webinar. I'm telling you a bit about my project where I analyze bacteria and biofilms with NAP-XPS. So biofilms, first of all, they are defined as bacteria embedded in a self-produced polymeric substance, which is called EPS. You see here a simple schematic of a biofilm on a substrate. So you have the rod-shaped bacteria, which are approximately 1 micrometer long, in this case, which is E. coli gram-negative bacteria. And they settle on the substrate and physically attach and form this network with this slimy substance in between them. The goal for the sample preparation I will show you is that we have a starting point for reliable characterization of bacteria and biofilms, and to provide a bridge between the microbiology lab and the lab where the NAP-XPS measurements are conducted. And in order to do this, we've been trying to keep it as simple as possible so that the last processing steps can be done eventually in the where the NAP-XPS instrument is also standing. So please note that this is only doable for class 1 bacteria, which are non-pathogenic bacteria. If you're working with pathogenic bacteria, then you need other sample preparation methods. Since bacteria are quite complex systems to work with for XPS, I have broken the system down to 3 different model systems. First of all, we have bacteria on silicon wafers, and these are planktonic bacteria without the EPS matrix in between them. And I have 2 preparation methods to distribute them on the silicon wafer. Then we have biofilms, which are grown on silicon wafers. And then as a model for the EPS matrix without the bacteria, we have various films of alginate and agarose, which are polymers. So to show you again the importance of sample optimization, I here show you 2 survey spectra. One is of a biofilm before optimization, and one is after optimization. They are acquired in 2 millibar water vapor. So before optimization, you first of all have also a signal from the silicon wafer. This is because the bacteria grow inhomogeneously on the substrate, so you also have patches without any biofilm. And then you also have a signal from sodium and chloride, which is from the washing buffer, usually called PBS. and you also have a phosphate from a phosphate in the buffer. And after sample optimization, you have a strong signal from oxygen, nitrogen, carbon, and phosphorus. I'm showing you 3 movie clips very soon. The first one, I show you how I transfer the bacteria from an agar plate to the silicon wafer. This is the simplest method, both for transport and sample preparation, because the bacteria are not immersed in any medium. You don't need any rinsing steps, and you obtain a very dense layer of bacteria. Next, I show you a movie from biofilm preparation. So biofilms are, in our case, actually grown in 6-well plate like this. And you put the silicon wafer in the 6-well together with nutrients and bacteria, and then they form a biofilm on the substrate. And they are also transported in the 6-well plate to the XPS lab. And then you need to perform some rinsing steps because the biofilm is immersed in this nutrient solution, and you need to do this without disturbing the biofilm. Now, biofilm growth is more complex than just the bacteria, but it's also more interesting. For instance, you can add antibiotics and study the interaction between the antibiotics and the biofilm. For the last film I show you, we have also planktonic bacteria, that is also bacteria without the EPS matrix. These were grown in a liquid solution and separated from the solution by centrifugation and transported as a bacterial pellet, which is really in the bottom here, on ice. And right before XPS analysis, I then dilute the solution a bit and distribute it nicely on a silicon wafer. And compared to the agar plate, you then get a very flat and homogeneous layer of bacteria, but you still need rinsing steps. Okay, so I'll show you the videos.
First, I carefully transfer the sample from the growth medium to a well filled with phosphate buffer and leave it there for 5 minutes. After 5 minutes, I transfer the sample from the phosphate buffer to water and wait for another 5 minutes. Finally, I dry the backside of the substrate with a tissue and adhere the sample to the sample plates.
Okay, so that was already the second video. Now I will find the first video, which is here.
Here you see a clean silicon wafer, which is already adhered to the sample plate with double-sided tape. On the side you see an agar plate with E. coli bacteria. I use a sterile spatula and swipe bacteria off the agar plate and transfer them carefully onto the silicon wafer. With this method, you obtain a dense layer of bacteria on the substrate.
And then the third video from the bacterial pellets.
Here I have a tube with a bacterial pellet. The bacteria were grown in liquid and separated from the growth medium by centrifugation, then gently rinsed 3 times with phosphate buffer and stored on ice for transport. This is now a thick bacterial paste, so I dilute it with 200 microliters of water and deposit a drop of the bacterial solution onto the substrate. The bacteria then distribute in a rather uniform layer. Compared to spreading out the bacteria from an agar plate with a spatula, this layer is thinner and more homogeneous, but it requires centrifugation and rinsing steps before sample transport.
Okay. So if you have any questions to the sample preparation, you can write that in the chat. We will now show some recordings of a biofilm of NAP-XPS measurements of E. coli biofilm in 3 different conditions, in 10 millibar, 5 millibar, and 1 millibar water vapor. So we start with, for all conditions, we have 3 scans and pass energy 50 electron volts. And this is just to give you a very rough idea of how it is to actually do the measurements and how long time it takes.
So this is kind of showing you how the real measurement would be. So we defined 4 elements: carbon, nitrogen, oxygen, and phosphorus, for the same sample at different pressures of water vapor. So Marit found out that water vapor would be very advantageous for the samples to be measured to prevent drying of the samples. And we show you each time the first scan of the element, and this for 3 different pressures. So you will see first spectra in the end, and then we will show you also a survey spectrum. Now you see the first carbon 1s spectrum of the bacterial sample, and the main constituents here is the carbon with different carbons originating from the EPS and the bacteria itself. And you also saw some signals from the potassium in the beginning. Now comes the oxygen O1s spectrum of the bacterial sample, and here we see that we have 2 separated peaks, one sharp peak which is corresponding to the water vapor, and then you have a second peak which is corresponding to the sample surface of the bacterial film. Say, since we got oxygen originating from?
Yeah, so oxygen also mainly originates from polysaccharides and also from phosphate groups. Compared to the carbon 1s peak, I will show some peak fits afterwards. These are a bit harder to get information out from, but very roughly you have the gas peak here, and then you have a broad peak where you have the left-hand side, you have groups from single-bonded oxygen, and here you have from double-bonded oxygen.
So the next spectrum will be the nitrogen from the sample itself.
Yeah, so the signal for nitrogen mainly comes from proteins, which are made of chains of amino acids. And you also have amine groups in various amino acids, but unfortunately we are not able to distinguish the amines from the amides. They are both at 400 electron volts. However, we also detect at higher intensities, we see also a peak from protonated nitrogen species, approximately 1.3 electron volts shifted towards higher binding energies.
Okay, and with that, after the nitrogen comes the last element at 10 millibar. This would be phosphorus. And there you see that the intensity of this nitrogen and phosphorus is both significantly lower than the main elements carbon and oxygen.
So I often, for data analysis, I look at the atomic ratios between carbon, oxygen, nitrogen, and phosphorus. And very roughly, after you correct it for sensitivity, the oxygen to carbon ratio is approximately 0.4. Nitrogen to carbon is 0.1 to 0.2, and phosphorus to carbon 0.01. So you really have a distribution there, and these kind of quantitative data you can also look up in the literature, where you have some review articles from freeze-dried bacteria, where you also can compare the elemental composition to our results.
Okay, now here you see the dramatic difference between the signal intensities at 10 millibar compared from the phosphor to the carbon. You can see it also in the overview screen of the different elements. After that, we will switch to the 5 millibar measurements in water vapor, starting again with the carbon 1s spectrum. So again, in this task manager of the Keystone software, we start in the spectrum group at 5 millibar and just push the play button to start the measurement in the same spot. And then we will see the first scan of the carbon 1s in the plot view.
So generally I do these bacterial measurements at 10 to 15 millibars. So we are interested in doing them in as high water vapor pressure as possible, because the biofilms are inherently in hydrated states. And the water vapor pressure, for comparison, the water vapor pressure in air is 23 millibar in 20 degrees Celsius, so it's quite close to relevant atmospheric conditions. Here we also again see better the potassium signal, and potassium is also a main constituent of the bacterial surface.
And here you also see the significant increase in signal intensity due to the reduced pressure, and you see here again the CO carbonyl components and acetals, the CH backbone of the bacterial sample, and the CO and CN bonded carbons. So the shape is pretty much the same as before. Now we switch to the oxygen 1s spectrum. Here you see that the water vapor related gas peak is lowered in comparison to the substrate or the bacteria film related O1s peak due to the reduced pressure at 5 millibar. But you see that it doesn't take too long to have a single scan of such a sample, where you also already see some features separated and can be analyzed. Here now the nitrogen 1s spectrum at 5 millibar, and you see that you see for all the other spectra also that they're a little bit shifted to higher binding energies. This is due to the environmental charge control, so the gas pressure is reduced, and that's the same what Andreas showed before on the PTFE sample. You see a slow shift in binding energy to higher binding energies due to a not as good charge compensation as before at 10 millibar of water vapor. But you see that the intensity is much better than before, or much increased. So this is kind of a trade-off between signal intensity, Photostat maximum, and condition you want to measure in.
So now we're back to phosphorus, and the main signal from phosphorus comes from the phospholipid membrane. As I mentioned, these are E. coli bacteria, and they are gram-negative. That means that they have a double phospholipid membrane with a peptidoglycan layer in between. And in comparison to gram-positive bacteria, these cell walls are much thinner and more fragile. So for the surface analysis, there's also important, you can distinguish gram-positive from gram-negative bacteria.
Okay, and last but not least, then comes the measurement at 1 millibar. Which is shown here, and starting again with the carbon 1s spectrum, and same as before, starting the measurement, and again see an increase in signal and a slight shift to higher binding energies due to the reduced charge compensation. As you will also see, the main shape of the carbon 1s spectrum will not change due to the decreased pressure. So the main shape is the same, the intensity goes up, and it's shifted to higher binding energies. But still you can use it for peak fitting analysis, but it might be that the individual components might show some increase through the set maximum. So again, you see the potassium peak here, potassium 2 peak, double peak. And now you see the carbon 1s rising. Pretty much the same shape as before. And as you also see, the shape in binding energy is not, it's 10-20 eV, so it's still okay. And you can use this carbon 1s peak to reference internally a spectra to this aliphatic carbon. Okay, then comes oxygen.
Yeah, now we barely have an oxygen peak from the water vapor, but it's closer in energy separation from the sample peak, so it's actually harder for the peak fitting to distinguish the two peaks.
So the gas line pretty much stays constant at the same position, but the substrate or the sample related peak shifts a little bit higher binding energy, so both of the peaks are not so well separated as before, but the main feature now is from the surface you are studying and not from the gas phase.
And now the sample is also less hydrated.
Yeah.
So it's good to know the different pressures you can measure in, but it's better to be at higher pressures and then you do more scans instead. Then we are at the nitrogen peak.
So now you see the nitrogen starting. Compared to the other two before. And now you will realize that there is a second peak in the nitrogen region, which is in the area around 409 or 410 eV, which is caused by residual nitrogen gas in the system. And then you see the main peak from the surface of the bacterial film itself, which is now much more intense than the other ones at 5 and 1 millibar. And this maybe could help to differentiate different nitrogen species in a not so intense nitrogen peak. Again, the last one is the phosphorus compared to the other ones. And also here you see the slight shift in binding energy, but you see the significant increase in intensity from 10 to 5 and 1 millibar. And with that, it's almost done. In the end, you will see that there's also a surface spectrum showing all the different elements. And with that, we hope we could demonstrate to you how this near ambient pressure XPS measurements of bacterial films can be realized in an easy way and also in a pretty fast way. If you think that we measured 4 different elements at 3 different pressures. Yes, now Marit will end this webinar or the slides and presentations with a short outlook of her work and this project.
Yes. So just summarize what you just saw with fitted peak, with peak fitted spectra. We know that the bacteria, the surface of the bacteria consists of polysaccharides, lipids, and proteins. In XPS, we detect that as carbon, oxygen, nitrogen, and phosphorus. But due to the chemical shifts, we can identify the peaks to some extent to these constituents. So with carbon 1s spectra, we have the aliphatic carbon from the long-chain lipids. We have carbon single bound to oxygen and nitrogen, carbon from the amine bindings, and also from carboxylic carbon. And these are also in accordance with literature from freeze-dried and frozen bacteria.
So these are from acetals and carbonyls.
Yes. So as a short outlook for what we want to do next, or what we are doing already, our interest is that we use this well-defined model system and take it one step further. Then we want to add antimicrobics and detect the vertical concentration profile of these elements. So antibiotics typically consists of elements like iodine, fluorine, silver, and chlorine, and they can be distinguished from the organic matrix. And for this, GCIB sputtering, or argon gas cluster ion beam sputtering, is a suitable method in combination with XPS. So that method, you are bombarding the sample with argon clusters, and the argon clusters then remove atomic layers of the sample, and then in between you acquire XPS spectra to detect the dynamics of, or the depth-dependent spectra. For this, we have a model system of povidone iodine. This is a very common antiseptic, which is used for disinfection and wound dressings, etc. You see the chemical structure here. So you have a polymer called povidone, and it's in a complex together with hydrogen iodide, and in contact with water, you release elemental iodine, which has the toxic effects. So let's just look at some preliminary results. Here you see survey spectra from 3 different sputter cycles. So before sputtering, after 44 minutes of sputtering, and after 64 minutes of sputtering. So before sputtering, you have a closed film of povidone iodine. After 44 minutes, you see obviously that the iodine 3D peak is lower in intensity, but the signal from oxygen, nitrogen, and carbon is approximately constant. And you start to see a signal from silicon, which is the substrate. After 64 minutes, you don't have any signal from iodine at all, and the dominating signal is from silicon. So here you see that there is a distribution of iodine in the film, and you can also monitor the film substrate interface. So with that, we'd like to acknowledge some who helped us with this webinar. That is Laura Shadow from SPECS, who did the video editing, Dr. Karin Schwibert at the BAM for helping me with the preparation of bacteria and biofilm samples, Sven Schröder and Elizabeth Wilnes at the University of Leeds, where I did the GCIB XPS measurements, and also finally the Metrology versus Bad Bugs project partners. And we also want to thank you very much for listening.
Thank you.
And now we are ready for some questions, if you have any. And if not.
Andreas?
Yeah. While you think of your questions, I would like to take the chance to thank Marit and Paul for the really great work that have been done here. It was a 3-year European project, and we were happy that we could be part of this metrology project and learn for the first time how you really work and measure biological samples, bacteria, and biofilms. We also learned a lot about that. And this was all done in the framework of the SPECS group, and also this webinar was done in the framework of the SPECS group. So some final words now about what is SPECS group, and please, I still ask you to think about questions. So far I don't see anything in the chat, so if you have questions later on, we will be happy to answer them. So the SPECS group is a house of brand, and one brand you have learned a lot about today is the Enviro brand. And the main product that Enviro is producing and selling is the EnviroESCA. The second brand under this SPECS group house of brands is Nanonis. This is a well-known and world-leading supplier of electronics, for control electronics for SPM, what is a MIMEA, and for transport measurements, what is a TRAMEA. And finally, as the center brand of the SPECS group, it is SPECS itself, and this is a brand that is already there for more than 30 years and producing everything what is surface analysis, like XPS, UPS, RPS systems and components, near ambient pressure XPS systems and components, scanning probe microscopes, deposition, preparation, and system integration technologies, and also electron microscopies like low energy electron microscopy, photoelectron emission microscopy, and momentum microscopy. And all of this together is the SPECS group. And if you are interested in learning what we are doing, please visit our webpage. What is the SPECS group? specs-group.com. And on this SPECS group webpage, you also find pretty many application notes. So if you are interested in what you really can measure with especially the near ambient pressure XPS techniques or the EnviroESCA, you will find a wide variety of these application notes and also a publication list. And part of the work that has been shown today was already published there. So if you need more information, please visit us.
Okay, thank you, Andreas. So I see someone is typing, but so the question is, how is the liquid sample station different from the solid sample station? So you mean from Andreas?
Yeah.
Okay.
So I will switch on the microphone. Maybe you should switch off. What is the difference of the different sample environments optimized for liquid samples or from the solid samples? Well, the liquid sample does, in the moment we are doing everything in one sample environment here, what means that when we would like to measure liquids, we just put a glass of water or a glass of liquid inside or a watch glass of liquid inside. And if we would like to measure solid to liquid interface, then we just put a solid into this, this container. But there are also optimized liquid cells with counter and reference electrodes and contacts and optimized contacts, outer contacts to, for example, electronic control systems like potentiostats, where you can do measurements really on battery setups. And for this, we also provide optimized transfer systems so that you can also transport liquids that are air sensitive to this by just bringing them in from an inert environment into the sample environment. So there are very different stations there that you can choose, and we are always happy to discuss on what your really needs are, because we can mostly realize especially something for you to introduce special samples or special containers into these sample environments.
Okay, thank you. So in charge correction, we showed the goals. So the charge correction here for the gold was, so this sample was grounded. So in this case, we don't need the charge compensation for the gold signal. And I don't get the full question. Is it possible to make charge corrections only between carbon and nitrogen, or is it possible to change correction from gold to other elements?
Maybe, so, is that a question about the bacteria?
No, I think it's, so you can use the gold signal to charge reference the.
Maybe I try it. Maybe I try to answer this, although I'm also not 100% sure. I think the question is if you can do it with each and every element. Yes, when you can charge neutralize a sample, then the charge neutralization is for all elements that are inside the sample. So it is really a homogeneous charge neutralization. And this means that you get a rigid shift of your elements with the pressure. So that means when you shift the carbon signal by 5 eV with changing the pressure, then you also will do so on all the other signals inside the sample. So it is, we did not find any sample in the moment that you could not charge neutralize. But as I said in the beginning, the optimized way of doing the charge neutralization is to look for, you just select one signal, and then you optimize the full width half maximum. If you do this, it is valid for all the other lines also. and then you might still have a residual shift of your lines with respect to the binding energy scale. And this is just then possible to rigidly shift all the lines by the same amount of energy to the really correct positions. This is what then is done in the final step. I hope this answers your question. Yeah, right. Shift will be the same for all the elements. Yeah, that's true.
So that was also for the PTFE sample, but Andreas only showed the fluorescent signals, so this would also shift the carbon. So you shift all of the elements in the spectra at the same amount. So this is not inhomogeneous charging over the sample. Okay, I see there's someone else typing. Not. Seems to be a longer question. And just to add up for this chart, okay. No, for this charge compensation. So we tried different gases and there was no big difference between, for instance, argon and nitrogen. But sometimes it showed that water vapor is working better than other gases, for example, with Maritz samples, and then it's a quite severe effect in the Fulvis-Held maximum of the spectra. And you can optimize the, for instance, the carbon monos 1s spectrum using water vapor instead of argon or nitrogen. Okay. Andreas will ask this because this is a...
No, this is in fact, we are not considering this. And the reason is that we think the charge neutralization really works so nicely and so homogeneously that we cannot imagine on why we should do that. And on the other hand, when you really consider that you would like to do ultra-high vacuum measurements and you would like to have to charge neutralize, then this would be in contradiction anyway, because at a certain point when you use the charge neutralizer and then you increase the gas pressure, the charge neutralizer would not work at a certain point. So we are not planning to do a traditional charge neutralization on the EnviroESCA. We are doing it on our other systems.
Okay, thank you so far for the questions. So, do we clean the... No, fortunately we don't have to clean it every time. As long as you don't dip in with the, so as long as you don't dip in your nozzle into the liquid, you don't have to clean it, but recently we had some samples which were not so clean or which was buffer. And if you dip in some buffer or something and then you take it out and pump up and evacuate the analysis chamber, then you have the residues from the crystals, from salts or buffer constituents like phosphates or other stuff. And then if you do it longer or if it's severe, then you're blocking the nozzle inside and then you lose intensity or you don't get any signal. And then you have to clean the nozzle, but this is also pretty easy to be done. You can take out the sample environment, which takes about 15 minutes, and then you just remove. So you have to break the vacuum, but you clean the nozzle just then with water or some other solvent, and then you just put it back. So this is not a big deal. So I think it's more severe if you go too far with the manipulator and hit the nozzle and then deform the nozzle. Then this is more serious. Then you have to exchange the nozzle as kind of a spare part or something. But in the day-to-day performance, I don't know, I clean it sometimes 2 times a week, and some weeks there's no cleaning because there's nothing happening. Depends on the sample you're measuring. Some liquids are more viscous and they are not behaving like water, for instance, but aqueous solutions are pretty easy and straightforward to measure. Okay, can you do
maybe?
So, okay.
Maybe I can contribute to this. We had a customer here in December and we're measuring a solid to liquid interface, and by chance there was a bubble coming up and the analyzer was drinking, it was an organic solvent, was drinking the organic solvent, and afterwards it was absolutely easily possible to measure again. So if it really happens that you dip in your nozzle into the liquid, you will have a short time when the pressure in the first pumping stage of the analyzer is a bit high, but as long as it is not salt-containing liquid where the salt is ending up in the ellipsoidal grid behind the nozzle, then you still can measure on after you pump it away. If really the salt is ending up in the grid behind, then you can take out the grid and you can wash it away, and then you can measure again. There's another question. Microscopic viewing. There is the sample environment already has digital microscopes inside, and we also have this digital microscope station, what is the Sample Explorer, and this gives you a lateral resolution in optical microscopy of about 10 microns. I would not exclude that it is possible to use one of the windows to have a better view. On the other hand, this is more in the sample environment when you are down in the sample environment, not so much in the measurement position, because there the angles are pretty flat that you have there. But in principle, it can be discussed if you could use something what is higher resolving if it is needed there. Will it always be a high-resolution optical microscope? I'm not optimistic, not in the measurement position itself.
Okay.
You're welcome.
So far, I don't see any further questions. So maybe there's another coming. So if there are further questions after the webinar, you are still free to write us an email or just contact us via the website. Yes, you could also, so we also have a Peltier cooling stuff, sample holder, where you could freeze or where you can cool down the samples for yourself, and then you could hold some freeze-dried samples also at, I don't know what is the minus 30 or 40 degrees, so it's not cooled with light nitrogen, it's a Peltier cooling element, but in general, you could also take aqueous solution, put a drop on the sample stage and cool it down and freeze the sample on the stage at minus some degrees, and then you can analyze them in an analysis chamber at a different pressure.
You also can do a nitrogen. Also the Peltier cooler is very proven concept for the near ambient pressure, but of course it is also possible to have a classical liquid nitrogen cooling there if this is really needed. So this could be a special sample environment.
Okay, I don't see any further questions. And with that, I would like to thank you for attending this webinar. I would like to thank Andreas for his contribution and also Marat. And yes, if then would come no further questions, I would end this webinar, and maybe we see again in a future meeting here at SPECS webinars. Okay, thank you.
Bye-bye.
Bye-bye.